Welcome back. We will continue our discussion on orbit. We have seen till now different types of orbits and the velocity, the orbital height and the time period of the orbit, how they are related, and what is called geosynchronous orbit, geostationary orbit, and other different types of orbits. Also, from the observer at the earth, which is we can call a earth station, which direction is in the satellite, that is the look angle to the satellite, the azimuth, elevation, how to calculate the distance from the observer to the satellite, which is very important for us because that will give us the delay of the signal from observer to the satellite to reach, or the other way. Similarly, whether the satellite is visible, at what angle, and from the satellite what angle the earth arc or earth surface, how much is visible. Some of the calculation, quick calculations we have done. Now, let us try to see that how do we raise the orbit or reach to the geosynchronous orbit. We are seeing that geosynchronous or geostationary orbit is quite advantageous, particularly those who are in India or near equator. For them it is very good because elevation angle is quite high, the disturbances from the local reflections or multipath are very low. So, that is quite advantageous, though other types of satellites, different orbits are also available. So, let us try to see how this orbit is reached and by different types of launchers. We will just try to see some of the pictures of the launchers. So, let us go back and see the basic planes of the orbit. This is the, let us say this is the earth and this is the equatorial plane, and for generalization let us say that satellite is orbiting in a different plane than the equatorial plane, and that orbital plane is making a inclination with the equatorial plane. This is the perigee and there may be apogee below. So, this is the position. For geo, the satellite velocity at geo, that is what we will calculate, that is geostationary orbit. The inclination what we have seen just now is 0. That means the orbital plane and the equatorial plane are same, on the same plane, and the eccentricity of the orbit is 0. So, there is apogee is equal to perigee. So, with these two conditions let us try to calculate orbital height and velocity. This is a circular orbit, time period is 1 sidereal day we have seen. So, it is 86164 second, and that constant mu is 3.98 10 to the power minus 5 or 398600 kilometer cube per second square. In this circular orbit, that is at GEO, what is the velocity? To calculate that, you remember that t square, that is orbital period square, in this case sidereal day square, is equal to 4 pi square r cube by mu. And from this, by putting the values of sidereal day and mu, pi is a constant, we get r is equal to 42164 kilometer. So, putting this r for calculation of velocity, we get velocity is 3074.7 meter per second, that is roughly about 3 kilometers per second. If you recollect our initial calculation, just rough calculation in a table, is at 40,000 kilometer, velocity is of the order of 3 kilometer per second. It is coming here. Remember this number. At this velocity, the satellite moves continuously in geostationary orbit. Now, let us go back to that particular picture. We have seen this earlier, that from earth some location a launcher has launched a satellite and launcher has gone out, ejected the satellite. Satellite looks like a cube here, packed condition, and it is put in a particular orbit which is here named as a transfer orbit. Now, We will term it as geostationary transfer orbit, GTO, but right now it is a transfer orbit. So satellite will move in this orbit, looks like it's a elliptical orbit where perigee is near Earth and apogee is far away from Earth. Okay, and then there is some rocket firing. Rocket is already there in the satellite. It's called LAM here, liquid apogee motor firing. At apogee it is getting fired, so and it's a liquid fuel, so liquid motor. So liquid LAM apogee LAM firing. With that you give some incremental velocity. It has in the transfer orbit, at apogee it has some velocity. I give some incremental velocity to that, so that perigee changes, apogee remains same. We know that calculation in the orbit, in elliptical orbit at apogee and perigee. So by changing firing the velocity here and changing this velocity, I can change the apogee and perigee height. Here it shows that slowly the apogees are changed, perigees are changed, and whole thing is made circular. And during this process, it start deploying the other peripherals of the satellite, that is solar panel deployment, antenna deployment, etc., etc. It goes on. So this is called orbit raising. Let us do some quick calculation. How much is that incremental velocity? Generally, it is done. It is put in a parking orbit, which is a circular orbit, and then it is geosynchronous transfer orbit, GTO, and then it is a geostationary orbit. In some cases, the parking orbit is avoided. Directly the launcher places it into GTO. Our INSAT launchers, they place the INSAT satellites in GTO. We will see all these things. So parking orbit is generally supposed to be a circular orbit, which is near to Earth, is low Earth orbit, and then it is fired and it is put in a GTO, geosynchronous transfer orbit, means apogee is at GEO and perigee is at parking orbit, and then here the thruster or apogee motors are fired, so that the incremental velocity it puts it into GEO orbit. So let us try to do some quick calculation of that. This orbit raising is done by the combination of motors and at the launchers and at satellites. It depends on the type and capability of the launch vehicle. Injecting into parking orbit, satellite uses perigee maneuver to GTO. We have shown that diagram earlier, and then apogee maneuver to GSO. A space shuttle is one of the examples which does it this way. Directly the launcher launch the satellite into GTO orbit, which is done by launchers like GSLV, that is Indian Geosynchronous Launch Vehicle, or Ariane, that is European Launch Vehicle. These are conventional way. They are directly put into GTO orbit, and directly into GSO orbit is also possible. Russian rocket Proton can do that one. So it depends on the rocket's capability how it can do. We will do some simple calculation. Of course, there are some pictures of Indian rockets. This is called SLV, satellite launch vehicle, small rocket, earlier days. Then with two small appendage rockets attached to SLV is called augmented SLV, augmented satellite launch vehicle. Then this is called PSLV, polar satellite launch vehicle, much larger. This is a workhorse of Indian Space Research Organization. It puts the satellites are normally put in the nose cone, and it puts into the polar orbit, that is the orbit is around the pole. For different purpose it is used. For remote sensing satellites normally it is like that. Then GSLV, geosynchronous launch vehicle, bigger than this. You can see the height, and here also in the nose cone put the satellite. INSATs are launched with this, and sometimes the ISRO people they call it GSAT because it is launched by GSLV. They call it the satellite, they call it GSAT. Satellites are inside this nose cone. And then the later versions of GSLV, which is not yet launched, they will have much bigger satellite. Right now this can take roughly of the order of 2 ton type of satellite. This can take, I was told that it can take about, it will be able to take about 5 tons weight of the satellite, and PSLV can take about 1 ton of the satellite roughly. These are, you can go to the ISRO site to get more details. But one interesting thing why I am showing the picture is you can see there are stages, colors you can see, at least here you can see it very differently, very clearly, that is, this is a separate rocket, this is a separate rocket, this piece is separate rocket, they are integrated together. Why? That is the question. Why multiple stage? That incremental velocity delta v is equal to the velocity of the gas, velocity of the exhaust velocity of the gas, and natural logarithm of 1 by 1 minus mf by m0. This is the mass of the fuel which is exited, and this is the mass of the container plus the fuel, I mean remaining fuel. That is, mf is the mass of the expelled fuel, and m0 is the mass of the launch vehicle including the satellite and remaining fuel. To get delta v higher and higher, you have to make the denominator as small as possible. Therefore, this should be as near to 1 as possible, but this mf is getting exhausted, whereas m0 is nothing but the container weight, which is a dead weight. This fuel goes out, but dead weight remains. Some reduction is there, but dead weight remains. So, it is better, how do we make these two near to 1? So, after some fuel exhausted, I remove some part of the dead weight. That is the trick. That is how it is summation of many dead weights. So, summation of many segments of the rocket. So, one segment of the rocket fuel is exhausted, that portion of the container also is exited out. So, therefore, the remaining thing is again quite high, near to 1. That is the trick. To maximize the delta v, we reduce m0. In multi-stage launch, each stage provides a thrust, and the dead mass of the emptied container is removed to reduce m0. Thus, succeeding stages need the lower thrust to achieve delta v. And the final velocity is sum of all the stages of delta v, what we get. This is the multi-stage. Now let us go back. That is just a additional knowledge we gathered. Let us go back to our calculation of what should be the incremental velocity required to place a satellite in GTO from the parking orbit, and let us define the orbit size as height as 560 kilometer, and incremental velocity required from GTO to GSO. When I say GTO, it is apogee at geosynchronous orbit, geostationary orbit. So, apogee is known, perigee is known here. So, GTO to GSO, and of course, for simplicity let us assume that it is on the equatorial plane. So, inclination GTO and GSO is 0. This is a very generalized calculation. In real case for Indian launcher, we have seen that directly from GTO to GSO we go. Please keep your calculators ready and do the calculation, though I am going to show it step by step, but just do not blindly follow, you must do your calculation. Parking orbit to GTO is done at perigee of GTO, and GTO to GSO is done at apogee of GTO. It is pictorially shown here. Initially it is put into a circular orbit, and then at perigee it is fired. So, this elliptical orbit is attained, and apogee it is fired, so that geostationary orbit is attained. So, velocity at the parking orbit is mu by h plus re, that orbital height and the radius of the earth. In this case, orbital height is 560 kilometer, radius of the earth we just assume 6378, and mu value is known. So, it comes out to be 5.6 roughly kilometer per second. This after decimal numbers, do not worry in your calculator, let me be some small error here and there, but it is roughly about 7.5 kilometer per second. That is at the circular orbit, that is parking orbit at 560 kilometer orbital height. Now, to create a ellipse with the perigee of GTO is equal to 560 and apogee of GTO as as geostationary orbit, we fire a motor. So, the velocity at perigee of that particular elliptical orbit, you put rp here. The rp value is the same as this, and the semi major axis is the ra plus rp, where ra is geostationary orbit. So, with that r plus rb by 2, and with that you get, where ra is this, you get the perigee velocity roughly about 10 kilometers per second. So, when it is moving at parking orbit, you have to give difference of these two to get into that elliptical orbit. Incremental velocity from parking orbit to GTO is 2.3 kilometers per second. And then velocity at apogee of that particular elliptical orbit, you can put RA, and velocity will be 1.6 kilometers per second. Whereas at GSO we have calculated earlier, the velocity is supposed to be 3 kilometers per second. So, this difference is to be applied, and the incremental velocity from GTO to GSO is 1.4 kilometers per second. Simple calculation, but you must try to do it yourself. Decimal numbers do not get much for it. It is just approximately to give you a feel that only this much thrust is to be given. So, the fuel expenses is not much at apogee if we try to do. But then we have assumed certain things, that the GTO and GSO are all same inclination 0 to equatorial plane, but in real life it does not happen. That is, the launching site has certain latitude, the azimuth of the launch is having some angle, and orbital inclination, they are related with this expression, that is cos of inclination is equal to sine of the launch azimuth into cos of the site latitude. So, you can see that when the azimuth is 90 degree, and when the latitude is at 0 degree, that is at equator, the inclination is 0. So, you can attain the equatorial plane orbit, but in real life on equator you may not have some launch sites, particularly the in India, that is Satish Dhawan Space Center, which is near Madras, a place called Sriharikota, slightly north of Madras, which is obviously very near to equator, but not at equator. Similarly, at South America there is a place called Kourou, from where European launches takes place, which is also very near to equator, not at equator. So, there will be some inclination from those launch sites, and that is to be corrected to put into the 0 inclination. People tried to put sea launch facilities also, it is available around the world. So, to make that I equal to 0, the correction has to be applied. You can see this particular picture, where this is the orbital equatorial plane on which our orbit should come, but right now the orbit based on our inclination, based on latitude, based on azimuth and longitude, this is having some inclined plane. So, the velocity on this inclined plane is this, and velocity we have to achieve Vs, that is synchronous orbit or geostationary orbit, is this. So, you can form a triangle and you can find out delta V that is required, which will equal to Va square plus Vs square minus 2 times cos of Va into Vs. So, for spending minimum fuel, the correction, the velocity as correction, the velocity has to be minimum at apogee. So, at apogee this thing is fired. So, delta V I is equal to this expression as I just now told, and we have calculated that Va and Vs for that particular problem, and the I can be found out from the azimuth and the L, and you can calculate with some numbers. I will try to give some assignment basis on this, and you can do the calculations. Let us see. Now, that is briefly about raising the orbit into different orbital plane and adjusting the orbital plane for GSO. But then once you put the satellite into GSO, there are certain orbital perturbation. Basis is that all these things we were assuming that in the whole world, in the universe, we have only two bodies, that is Earth and that satellite, which forces are acting on each other, and Earth is a sphere, satellite is also a sphere, and the center of mass is at the center of the sphere. Those type of assumptions we have done. But real life, it is not like that. We have large natural bodies like sun and moon and other things. So your orbit will be perturbed. So let us look at the perturbation effect. Just now, as I stated, Keplerian orbit parameters assume that Earth and satellite has perfect sphere and no other force acting on them. In reality, it is not true, and that may give erroneous estimation of the orbital parameter. So non-uniform, one of them is non-uniform Earth gravitational field. It is non-uniform. You can quickly intuitively say that there is a lot of ocean body and land mass which are not uniformly distributed. Then there is the effect of sun and moon, their gravitational field. Then there is a solar radiation pressure. Solar radiation is putting some pressure on the surface of the satellite, which has solar panels. And if it is lower Earth orbit, you will have atmospheric drag, which will slow down the orbit. These are some of them. Let us look at each of them very briefly. Equatorial radius is not always constant. It is slightly bulged at the equator. Now, non-spherical shape, the average polar diameter is less than the equatorial diameter. I have taken from some books, that is the average equatorial radius is 6378, the other one is 6356 at the pole. It is different, that is what is important. Then Earth gravity at the equator is 9.78 meter per second square, at pole is 9.83 meters per second, taken from some books, all these things, but it is non-uniform, that is important. So therefore, it leads to non-uniform Earth gravitational field around the Earth, and due to this, force on the satellite varies on its satellite position. So this additional force tend to drift the satellite from the intended location, and it will either accelerate or decelerate. It was found out by a lot of experimentation and measurements that there are certain stable locations and there are certain unstable locations. Now, the stable locations are 75 degree east. Fortunately, India center is almost like that, I mean on that same longitude, and opposite side there is 252 degree east, and unstable position is 162 degree and 348 degree east. Now, at stable point, if there is any perturbation happens, it will make the oscillate to drift back to the stable point, any side it moves. But at unstable point, if it try to drift, one more thing you can you can see that these are exactly not 90 degree apart, because it's not a sphere. Earth is not a sphere, it's not 90 degree apart. So any perturbation at unstable point will drift it towards the stable point and oscillate around it due to inertia. So these movements are on the equatorial plane, so it is called east-west movement of the satellite. That has to be corrected, keep it in position. Now let us look at sun and moon. Earth is orbiting around the sun on a plane which is not the plane of the on which sun revolves, which is making some 7.3 degree angle. Similarly, Earth equatorial plane and Earth orbital plane around the sun are 23 degree roughly. A satellite is on the equatorial plane, geostationary satellite. Moon creates a 5 degree elevation with the equatorial plane of the Earth, and based on their position, that is moon, sun and Earth, there will be some force acting on the satellite. You can see that the force acting on the satellite can move the satellite northward or southward. So, this is called north-south movement. What I said is listed here. Ecliptic plane is the, that is Earth orbital plane is around Sun is 7.3 degree. Earth equatorial plane is 23 degree inclined to Earth orbital plane around the Sun. Moon's orbital plane around the Earth is 5 degree inclined to the Earth equatorial plane. So, net gravitational force due to Sun and Moon is not on the satellite orbital plane. So, it will change the inclination of the satellite. That net force is roughly about 0.8 degree per year. So, operators they keep initial inclination higher, so that automatically slowly, because it is a very small number, slowly it gets adjusted to save the fuel, otherwise you correct it. This is called north-south movement that needs to be corrected, and change in the inclination needs 10 times more thrust, that is north-south correction needs more fuel than east-west correction. Other things are atmospheric drag. When it is low Earth orbit, the atmosphere resists the movement of the satellite, that reduces its velocity in the orbital plane, and due to friction the body temperature of the satellite increases, it may burn. Normally satellites are launched above 180 kilometers, they are not brought below 180 kilometers. This is just a rough number, it is not a very precise number, because the atmosphere density is different at different places, different time, and most of the LEO satellite orbit is 1000 kilometers of the Earth. There is a solar radiation pressure which is proportional to the surface area projected towards the Sun. Its effect also will make the north-south movement. So, with all these things, the operators they think of a virtual imaginary box which is called station keeping box, which is a height of 72 kilometer, and sides are from the center of the Earth. It is about plus minus 0.1 degree for C band, plus minus 0.05 degree for Q band. These are operational arrangement, but it creates a virtual boundary on which satellite is allowed to drift, and when it reaches the boundary, on board satellite there are some rockets which are fired, or thrusters which are fired to bring it back within this box. It is called station keeping box. So, you can estimate for this degree how many kilometers it will be for different type of band. At the end of the mission, that is when fuels are exhausted, then it is moved away from geo orbit 150 kilometer. That is when we say satellite dies. Actually satellite never die. This actually the electronics are always alive, only the fuel is exhausted. So, some fuels are kept to move it out, or called deorbiting of the satellite. So, we will we have seen that how the orbit moves and perturbation. We stop here to continue in the next session about further effect of the orbit on communication system. Thank you.